Welcome to Flat Earth Debate Special Edition. In this particular episode we will talk about the WGS, or World Geodetic Survey 1984, and its uses. We are joined by Chris, Shane and Anthony. How you all doing, gentlemen? You all good?
Aye is good.
Hey, is back.
Excellent.
Doing well.
Excellent. Now, we've been talking a little bit off air, and we got to the namesake, which is 1984, and the doublespeak that goes along with it. So maybe that's the appropriate place to start, the doublespeak that goes along with this surveying system.
Yeah, it's an interesting way to, the terminology in these things is what kind of gets me when I start thinking about this stuff is that, they call it the World Geodetic System. And then we just, you look at the definitions and it starts right off with, right off the top with WGS 84 is an Earth-centered, right? Earth-centered, Earth-fixed terrestrial reference system and geodetic datum. Well, that means that's geocentric and it ain't moving, right? That's the first thing you notice right off the top. And then you think, well, okay, so what is it based on? If it's not moving and it's Earth-centric and geocentric and not, it's a fixed reference frame, then what's it based on?
I'm sorry, are we live now?
Yeah, we're broadcasting this.
Oh, right, okay, because I can't find you.
Yeah, so it's, you're going to have to see, okay, what is this entire thing based on? Well, it's based on, gravity and geomagnetic fields. Well, that ought to be a hint, I think, right? Of a spherical ball spinning in space. It's based on gravity. So why would you call it a global positioning system? It should be a gravity positioning system if it's based on gravity and time. And you just keep digging through it, and you go, okay, so Earth's center of mass being defined as the whole Earth, including oceans and atmosphere. Then they define it in terms of gravity back to 1984, right? And as you kind of keep reading through, it gets more interesting as you go through it. The coordinate system, let's see. Geometric center. Generated by using. Okay, here's where it gets interesting. So the WGS 84 geodetic coordinates are generated. So generated, right? They're not actually anything, but they're generated by using its reference. This is a reference, fictional reference, ellipsoid. Okay. What's an ellipsoid? And how do they come up with a definition? What does it look like? What are its dimensions? In this particular one, you won't find any pictures. But I'll go through it a little bit so you can see that it matches the next reference that we use here. Semi-major axis flattening factor. Oh, we got a flattening factor. Well, that's interesting. What is a flattening factor? 1 divided by f. 298 seems like a rather large number. And how do we apply that flattening factor to gravity? And where is this gravity? So basically what they did is they took it and gave it an epoch to a certain year. So you have a point in time that's experiencing velocity. So obviously this thing is really complex to try to figure it out, because if it was a simple sphere, just a few dots on a sphere measuring land masses on the surface of a ball, anyone should be able to stretch a tape across it and do some dimensions and come up with a map that works. It shouldn't be this complicated, obviously. So let's have a closer look at what this thing really is when you take a picture of it. This is the reference Earth model, WGS 84. And here is the spheroid, ellipsoid that's being referenced in those equations. And let's see, it's not too hard to figure out. We got a C value and an A value. referencing this ellipsoid, spheroid. So the formula we looked at earlier for the flattening factor, which again, it's repeated, so this is the same number, around 300, 1 over 300. It says here to take A operations, so we take A minus a C. So now we've basically subtracted and lost that number completely. So we no longer have a vertical radius, we've subtracted it, and then divide it by A.
Can you repeat that, because it broke up a little bit at the start of your sentence?
Well, when you just look at the basic math here, it's A minus C. So you take the A, subtract the C, and then take that value and then divide it by the A again. So it's pretty easy math. You can see that that is completely canceling all this out, essentially. It's a derivative factor. So I was like, well, this is an interesting diagram, but does it hold true when you do this formula and plug in the numbers using these numbers, right? The meters times the meters. Basically, you take this one, take this number here, and subtract this number here, take that value and divide it by itself. Essentially, almost is how that works out when you do the math. So I'll switch the share screens here and show you what that actually turns out to be when I did it in the software here. Switch screens. It turns out to be this, more or less. Because you can see I did it to scale, of course, but I took the 6,378,000 kilometers on the X and Y axis. And in the Z value, I plugged in that formula. A or C minus A divided by A again. And it works out to 3.293. So in meters, and this is to scale, right? So essentially, you end up with a flat plane in a sphere that's been flattened down until it gets down to this value in a cross section with a thickness of 33 kilometers. So take those numbers as you will, right? 33 ends up being the magic number.
Right, can I ask a couple of questions?
Sure.
Tim came on this morning, and just before sniping me, because he's a bitch, he was talking about the stars. How do the stars relate to this?
Well, they're just plotted. The stars are plotted to a celestial sphere. We're on this plane of whatever this dimensional plane of existence and inertia is, and the stars go around us like they do.
But he says there's 2 rotation points. Now, to be honest, when I've looked into the 2 rotation points, they don't seem to be perfectly spherical. One appears to be, the other one not. Do you understand anything about how the 2 apparent celestial rotation points that they call the pole stars interact with this?
Well, I don't know. There's an offset for sure. Like when I looked into the stars, the North Star would be the pole star, and the South is actually an offset. So it's an interesting set of mechanics that's going on there. It has more like fluid dynamics than it does physical properties, from what I can tell. It appears to be more of as if it's in some sort of on the surface of a Gaussian sphere, some sort of electromagnetic anomaly. It's flowing like fluid more than it is physical. When I looked at the the W map, which is the cosmic microwave background radiation map, and the CMB map, and I looked at all that.
So is there 2 rotation points in the night sky, one at the North Pole, one at the South Pole? And if there is, how does it work on this?
This isn't set up to actually show it, but this is just WGS84.
Right.
Just while we stick with the WGS84, so just so I can get it in my head exactly what's happened. So we have Earth represented as geoid Earth, which is a spherical Earth. We'll get to what a geoid is in a minute. I don't know if Anthony can bring up the definition. But you start with that, and then you apply... So here, perfect. So here is the geoid Earth, and it has on its surface, what's it got on its surface? Continents, stars, what's on the surface of the geoid Earth? Chris?
Well, it's kind of hard to say. Like, they call it a geoid, right? So it'd be a surface that's an irregular surface. Like, if you think in terms of geoid, it'd be like a up and down surface that's has no constants. And then they take this and they just basically draw this. They bring it all down to get something to reference as a flat plane. Then they project everything out. You're surveying to the stars as a reference point in time. Right? And then that's all projected down to a map. The maps can be anything. The map can be a flat square map that actually maintains distances, or a circle, or anything. It would plot out pretty much the same.
Sure, but as a surveyor, so as far as you're aware, as a surveyor, you're on a globe. So you're on, let's say you're in Central America or North America. Keep it easy. You're on that point in your mind on a sphere. So you'd find that point on the geoid Earth, correct?
Yeah.
And that would be
basically you would have to survey it relative to your datum point, survey it to the stars, bring it down to the geoid, and then flatten it.
Essentially, you take your position on the globe, you apply your position relative to the stars, and then you apply your flattening factor to get your actual position. And that would be what you have in front of us now. This is your position relative to everything else on this datum.
Yeah, it's basically it'd be the same as if you took this sphere, applied the flattening factor, and squashed it after you surveyed it. Right? You're just doing this. You start out here and you bring it down. Right. That's all that's happening. So once you apply the flattening factor, it brings it all down to this datum, which is 33 kilometers at its thickest point.
So you're referencing a flat world, and this is what the people who produce the Ordnance Survey use. This is the WGS-84, which is commonly was referenced by Rumpus as the better model of Earth. So this is beyond Google. We are now at the point in the debates where the people who are for the globe, are under the delusion that we live on a sphere. They want to use the Ordnance Survey maps, and the specific datum that was referenced in terms of a global referencing system was the WGS-84, this 1984 based referencing system, which, when you apply the maths, flattens it from a spherical Earth down to what you actually use when you do your surveying, which is a flat disk, 33 kilometers in thickness.
Yeah, it ends up being, it's flattened, and it's either flattened equidistant azimuth will work, or a flattened flat square grid. It works out the same. Yeah.
Right, they're both based on the same thing, i.e.
basically the same thing, yeah.
Yeah.
If I switch screen or window here. Stop sharing this one. Because I go back to that WGS-84 standard.
I have to reshare your screen again because it's completely stopped sharing.
Yeah, I gotta bring this up here if I find another. The reference I was going to go for here was DRF 2008. Basically, we'll end up kind of going around in circles as usual, but this is the way it does work when you survey this stuff. This one here should be. Right, so we saw back here where it references these international standards. You apply that flattening factor. And this one here, I think, references ITRF 2008, which is the International Terrestrial Reference Frame, essentially. ITRF reference frame. And you see that this one, it refers back to WGS 84 standards again. And you end up with this. Right? So basically everything comes down to these points. And it's interesting that they reference them as basically, 2 centimeters. They're velocity points where the whole thing is in motion. Right? It's just never stops moving, essentially. So I can understand why they did things the way they did to establish that standard using a center point of the mass, basically at a certain velocity, right? Mass times velocity to kind of get somewhere locked in time, because it never stops, right? It's just kind of undulating surface in frequencies, but it looks of it.
Okay, so you've got this, is it ITRS map? Would that be a valid way to phrase it?
The ITRF is the International Terrestrial Reference Frame 2008 Velocity Field.
Okay, I'll rephrase it slightly, because what I'm going to drive at is, earlier you're using an azimuthal equidistant projection, a circular map, and this is a square map. And in terms of referencing for surveying, I just wanted you to kind of detail the difference between the two relative to Earth.
Well, they both end up being pretty much the same, except the square map maintains distances between points on a grid system, so the distances are accurate. The azimuthal equidistant, it's still at the North Pole. It uses basically a coordinate system based on degrees, right? So things at the north come together and things at the south expand. So it's, although they say it's equidistant, it still has a deviation from the land masses and sizes. It distorts, as does any map applied to a sphere, right? Right. All maps are projections, and they're all distorted. There's actually, I can't think of any working map that's 100% accurate, regardless of what you do.
Now, in your experience, you've had to apply these datum points, correct?
Yeah.
And as a surveyor, or whatever position you were held in at the time, what would be the process in terms of your what I want to try and detail is how somebody who is in the frame of mind that I'm sat on the outside edge of a sphere, how does somebody go through this process of flattening something, and the way we've just demonstrated, it's obvious that it's becoming flat. And how does somebody who's surveying not appreciate the fact that they are actually surveying to a flat plane? That's the first part. And the second part is, once they are actually surveying the land, how does that reference back to this datum, and what do they actually do? And if I say the word level transit, I'm sure you'll know where I'm going and what I want you to explain.
Yeah, like if we were on a project, normally you would set up, well, they call them, gravitometers, to establish your local datum to your local coordinate system of the town, city, or wherever you're at. And you just set them up and you let them go for a week until they kind of, they calibrate themselves. These days, they use this constant velocity, and you establish where you are as far as in motion as a point in space and time. And then from there, you just drive a stake in the ground, essentially, measure that to a pin, call that your starting point, and then from there on out, it's all flat. Right? It's all level transits from point to point to point. Right?
Okay, so just to summarise, so once you're actually gaining one single position in reference to where you are on this flat plane, that's all you do in terms of referencing the WGS 84. You get your exact point compared to the geodetic reference points on this flat plane that you've flattened.
Yep,
but from there on in, you then said from there on in it's flat. So what do you mean?
Well, every shot you take is you level your transit, take a straight line of sight to your target, measure the angular distances as far as the distance to the target, as far as the elevations and angles, and calculate it out. And then you just survey it using straight line, Euclidean trigonometry. Right.
Okay, in one of the conversations we had, you said that if one of your surveyors under you was not to level his transit, you'd probably get sacked. So what is leveling a transit?
Well, you set it on a tripod and you level it in your XY. Well, you level it on the X-axis, make sure it's level on that X-axis, and level it to the Y, and make sure that the bubble remains centered basically centered with the zenith, right? And that's leveled in 3 planes. So if you spin the transit around, right, it doesn't go off its level. So you can spin it around in a circle forever, and it remains level in all. It's just on a flat plane in 360 degrees, level in all directions. So everything you measure relative to that point is accurate in its elevation and distances.
So in the same way as if you were to level your transit with a camera, you could physically look out to the horizon, spin it round and around and around, and it would never waver, it would never go up or down in terms of what you would see on screen in that camera.
That's correct, yeah.
Right,
yeah.
so it's
you
essentially...
look out to the horizon line at the vanishing point, spin it around 360 degrees, and it's a level circle all the way around you, level plane to a vanishing point.
Sure, because in the QED demonstration, one of the things you did with the failed globe model was demonstrate that with it being a spherical Earth, when you levelled your transit, you would observe curvature. Correct?
Yeah, that's right. Yeah, if you're on the point of sphere, right, and you have your level transit, like say top dead center at zenith, like at the very top dead center on a spherical surface, level your transit, and then spin it around in a circle, you would see drop. Essentially a curved line going in all directions from where you're standing at a point. Everything would curve down and away from you in all directions, 360 degrees.
So to put it another way, based on a sphere that is 24,900 miles in circumference, if you were a surveyor, you would see curvature when you were building things.
Well, of course, yeah, absolutely.
As a surveyor,
and
did you ever
to make matters worse, I mean, if it was spherical the way... if it was spherical to those dimensions of 8 inches per mile square, for example, if you built a building with, say, for example, 100-meter foundation square, like a foundation basement, and you took it up 1,000 meters, essentially by the time you got to the top, to maintain, supposedly gravity to this spherical surface, you would actually end up widening the building as you rose. But we don't build things that way. We bring them to a point to bring it, to spread your weight and mass, right, evenly over the foundation. But in theory, if it was the other way around, you'd actually widen as you went up. It makes no sense if you're trying to maintain a center of mass to a fictional center on a ball.
Okay, so back to the starting point of my question then. So when you were, I assume you've levelled hundreds, if not thousands, of transits, but when you were doing so as a surveyor who thought he lived on a globe, how would it be the case that you wouldn't notice the flattening factor reducing your observably flat world that you're surveying? How did you not notice that you were doing that?
It's just training, it's just, you're trained to do it a certain way. You follow your procedures, you calibrate your equipment to a local standard, and you just do your job. Right? You just don't second guess it. I guess we adopt it when we're 3 or 4 years old and we forget about it. That's it. You just never question it. How many millions of people fly in an airplane, look out at the horizon, and never have the second thought that it might not be around, right?
Okay.
It might be flat, right? It's just, that's a question I can't answer. I don't know why that is.
There was another slight bit of confusion with a globe defender that basically demonstrated the mathematics to be reducing the sphere by 33 kilometres. And again, as I say, as a professional surveyor who has used this data in your day-to-day business, how would you react to somebody who was under the delusion that the flattening factor doesn't actually reduce the geoid down to a flat plane, but in fact just reduces the sphere by a tiny amount?
You just go do the math. Go back to this, back to the diagram and take the A, subtract the C, put those together, and then divide by A again and see what happens to these dimensions. Plug it in a calculator.
Right, so there's someone in chat called Halsoy, and I've called him. He said that you've, quote, and I quote this, so don't kick me for swearing, Chris has fucked up the maths. And I've called him on it. I've invited him on to challenge you to see about where the maths is wrong. And all you've done is input the values onto the what's it called, the CAD system, right?
Yeah, that's all you need to do. Yeah.
So I don't know how you could mess up the math.
Which is the radius. Take A, which is the radius of the sphere. Subtract C from that A, and then divide it by A again, and see what happens to these two numbers. You can only work with A and C.
So
anybody can.
I'm going to I'm going to challenge Halsoy in front of everybody to do exactly this and show us where it was messed up, because he doesn't want to come on and challenge it face to face. So he's got time to go and show us where it was miscalculated and where that response or where that reaction was the response of human error. Halsoy, there's your challenge. And whilst we're here, I just want to ask the question that I'm sure a lot of people are thinking of. What is a geoid?
Yeah, that's a good question. I'm pretty sure you can dig out a definition, Wikipedia or dictionary. Here we go.
Right, on screen, I've got this word geoid, right? It claims to be a hypothetical solid figure. Okay, so that means it doesn't actually exist. It's hypothetical. So that seems to me a problem. But it's a hypothetical solid figure which surface corresponds to mean sea level, and its imagined extension over or under land areas. So basically, Chris, what is this trying to describe? A hypothetical solid figure whose surface corresponds to mean sea level. What is it actually describing? This sounds to me that it's talking about nonsense. Is it talking about something that's real, or is it something? I know what hypothetical means, and it's saying it's a solid figure that's hypothetical. So right, let's paraphrase this into the iron core. That's a hypothetical solid figure because it's supposed to be the iron core of the Earth, and that's supposed to be solid. Whose surface corresponds to mean sea level and its imagined extension over or under land areas. So what are they actually referencing? Are they referencing a mesh that goes under the surface of the Earth, the crust?
Well, it's a fictional surface, yeah. It doesn't exist. It's imaginary, right? It's a flattened ellipsoid that's convenient for surveying too, and makes the math easy. That's all it does.
Again,
I'd like a baller. I'd like a baller in this case.
Hypothetical means hypothetical is hypothetical, right?
Yeah.
Like go to your Google, open a tab there and just look up, Earth figure, right? The term Earth figure, and see what it renders for you.
Just for the audience's benefit, just while you're doing that. So what we are actually searching for here is the more accurate globe model. So we are told that Google Earth isn't sufficient, isn't accurate, and isn't fit for purpose when studying the heliocentric Earth globe-shaped model. Now, okay, I don't know why that's up.
I think the best part of this topic is that Pinhead comes up when you search for
Earth figure. Yeah, exactly. Yeah.
Amazing. Yeah. But yeah, so this is the better representation of Earth, and we're basically pulling apart how this more accurate and apparently more credible version of a model of Earth actually works. And this is why we're explaining that it most definitely does apply a flattening factor, bringing Earth down to a flat plane, 33 kilometers in thickness, and also that the actual model itself is hypothetical in nature. So the world that you believe you live on, the model, let's be clear about what it is that you think you live on, it's a model. That model is a hypothetical thing. So there we go.
So let's just be clear. The challenge on the maths is to Halsoy to show why the maths was done wrong in any way you wish, but show what the mistake was and how it actually should be. And then you can talk about what this geoid thing is that is hypothetical. I mean, you tell me what this is, because this hypothetical thing is a bit like the curvature, it appears. It's, assumption, like based on the apparent curvature of the Earth, we should not see things, and it appears that we can see things. So Halsoy, go and find out what the maths is supposed to be and demonstrate it so we could learn from your expertise on how we got the maths wrong here. Okay? Don't call nonsense unless you can show how it is nonsense. And given that you failed to stand up to the mark when invited in, then you can demonstrate it in the next week. Show us how it was done wrong.
Yeah.
Just to summarize, though,
the whole thing for me, like it really kind of gets me is the WGS84 and all these ITFR standards and all this stuff. They always go back to gravity, right? An unproven theory, right? But they use it as the center point of these objects of mass, and they call it a gravitational center in time, right? It's just a pinpoint, and it's a complete work of fiction, right? The whole thing is based on this theory of gravity. So Einstein to the rescue once again, right? right? And then when you look at Einstein's theories, well, he took all rotation and all mass and basically all movement out of every system and just made it a imaginary reference frame and, the special theory of relativity. It's now everything just becomes relative to itself and it's completely meaningless, right? Which is essentially, that's what happens when you apply a flattening factor and subtract all the actual dimensions out of it and make it a flat reference frame. That's why they call it a reference frame, right? When they define it, it's a reference frame. That's it. Imaginary, right? Right back to the square one.
And just in case anybody wonders, Halsoy appears to have gone very quiet, so I'm going to delegate the authority to Twitwit. Can you make sure that he finds out, please, that Halsoy finds out that he's got to challenge Twitwit? Thank you.
Has Twitwit become our secretary in chat? I love it.
Delegated secretary.
I love it. I just want to summarise then, because then we can round out. So basically, we start out with the representation of the Earth, a hypothetical representation, and that is depicted. Let's just change my screen slightly. Bear with me. There we go. So that is depicted here. This is the geoid Earth. So this is where we start with a hypothetical thing represented.
I can't see what you're sharing there. I don't see it on the screen. Yeah.
And then if we can go to Chris, if you can screen share and then just go through once more what happens to that hypothetical geoid so that it can be put into practical application for referencing the flat plane that planar surveyors actually observe when they build things. So I don't know if you can screen share that again, Chris.
Share screen. Back to this. See if that'll work. There you go.
Beautiful. So that's
basically it. Yeah.
This is what we end up with. So it applies a flattening factor. The maths has been up on screen a couple of times. A few people have said that the professional surveyor is wrong in terms of how he's applied this on multiple occasions to build things. However, this is what happens. This is what it becomes. So this is the flat plane of the WGS 84. This is what the guys who think they live on a globe now want to use when they're referencing their heights. Seems like the globers, through this debating process, have taken their first steps onto realising that the Earth is in fact flat. Anything you guys want to add before we round out?
Thank you, globers.
Well, it's one thing we get back to the gravity thing. So I always like to go back to square one. So you start back at a center point of gravity, and then around that you put a liquid sphere of hot molten iron at its center, which somehow generates its own electric field from absolutely nothing in order to generate a magnetic field that supports all life on Earth. However, molten iron, like anything, the hotter it gets, the less it will conduct, because it will not conduct unless it's above its Curie temperature, cannot maintain a magnetic field. There's a distinction between conduction and maintenance of a magnetic field. Right? And so the more energy you put into a conductor, and the hotter it gets, the resistance would increase exponentially, and thus carry less of an electric field in order to generate a magnetic field. It becomes a self-destructive impossibility having a molten iron core around this so-called center of gravity. And I would just leave it at that. It's not there's no evidence or proof of any such self-generating, self-sustaining dynamo and perpetual energy machine that I'm aware of.
Anything you want to add, Sleeping Warrior or Ranty?
Yeah. Paul Voigt claims that the Earth self-perpetuates, but we're still waiting for evidence for that assertion to be proven to be true. And as it stands right now, he claims to be a physicist, so would have access to details and journal references and a plethora of information about that claim. Yet he's produced nothing to date, and I'm going to keep reminding people of that because it's nonsense. If you haven't got any evidence of your assertion, Paul, then the assertion can be dropped. It's that simple. However, I'm going to keep reminding people that you claim that you have evidence to support that and keep not producing it. Ranty?
Yeah, so how long has this been going on now? It must be, 2 months that you've been asking for this? and he hasn't produced a single shred of evidence for this. As regards the presentation tonight, I think you've said it all. So, fortunately, I've had to say nothing.
Yeah, it's been.
I just like the geoid is a hypothetical solid object. I think that's great.
I like the flattening factor. I like the fact it's flat when they actually use it.
I'll tell you what I'm going to do. Let's round out with the definition again from Google for geoid. A hypothetical solid figure whose surface corresponds to mean sea level and its imagined extension over or under land areas. Hypothetical solid figure.
Yeah, hypothetical. And with that, I think I will say a massive thank you, first and foremost, to Ranty, Sleeping Warrior, and Chris Monk for joining us on this WGS 84 explanation. If you've not done so already, be sure to like, comment, share, and subscribe. I've been Nathan Oakley, and I will see you all in the next video.